With these practice problems, we need to determine whether the series converges or diverges, and just to get used to it, we want to identify the test that we're using. Although on the exam, you don't have to actually identify the test. So if we look at problem number 31, we have a couple of choices here. We can look at the nth term test, which is always a good one to start with, all right, which is basically saying the limit as n approaches infinity of our series. Well, if it does not equal 0, then we have a series which will diverge. And in fact, this series, if we put -1 to the n right in there, that will not equal 0, all right? Because what ends up happening is it toggles back and forth between -1 and 0, -1 and 0, so we don't get a limiting value, right? It does not converge to 0 in that regard, so we have a diverging series. Another way of looking at it, perhaps, is the alternating series test. With the alternating series test, because this is alternating and we're technically multiplying it by 1, that can be considered our u sub n. So we have the alternating part, and then the terms must be decreasing. Well, the term's always just 1. So again, the alternating series test, we're showing divergence. With 32, we have ourselves a geometric series. We are multiplying by 2/5 at all times, so r is equal to 2/5, which is less than 1, so therefore this converges by the geometric series test. With 33, we see exponential functions and factorial. When these come into play, quite often we're looking at a situation where we want to use the ratio test. Right. This is a powerful one and one which helps us out the most. So in this situation, we have the limit as n approaches infinity. We have to take the n plus 1th term and divide it by the nth term, which means we're going to multiply it by the reciprocal of the nth term. So this is the nth term. The n plus 1th term would be 2 to the n plus 1 over the quantity n plus 1 factorial. So again, we're going to divide that by this term, which is the same thing as multiplying by the reciprocal. We have to now find this limit. This is going to require us to do a little simplification. If we look at 2 to the n plus 1, we know from our exponential rules that this is the same thing as 2 to the nth times 2 to the 1st. We know that if we have the same base and we're multiplying, we just add the exponents. So we're going to write it in that regard. Factorial, which I believe we talked about in a previous video, but factorial means that, for example, let me just go over here on the sidebar here. If we have 5 factorial, that's equal to 5 times 4 times 3 times 2 times 1. And 4 factorial, well, that's 4 times 3 times 2 times 1. So if we're looking for 5 factorial, another way of looking at it is 5, right here, times, and then we have 4 times 3 times 2 times 1, but that's just 4 factorial. So 5 factorial is actually 5 times 4 factorial. So if we have n plus 1 factorial, that's n plus 1 times n factorial. And that's exactly what we're going to do right here. We're going to make this the quantity n plus 1, oops, I'm going to go back to the black pen here, n plus 1 times n factorial. Now the reason for these two rewrites is that now we can eliminate some values here. We can eliminate our 2 to the n's, and we can eliminate our n factorials. So now we have the limit as n approaches infinity. We are left with 2 in the numerator, and we're left with n plus 1 in the denominator. And that's a limit that we were able to calculate many years ago, or many months ago, I should say. That limit is equal to 0. We know that with the ratio test, if the limit is less than 1, then we have a series which converges. 34. This is another situation where it's a good idea to use the nth term test. Right? So if we take the limit as n approaches infinity of cosine n, all right, well, we know that cosine is a wave function which moves back and forth between -1 and 1. It does not have a limiting value. All right, so the limit does not exist. Since the limit does not equal 0, the nth term test tells us that this series diverges.